Yeah. So we'll see how we go. Cool. So the subject of today's lecture here is about lossy image compression that builds on the work that we did last week, which was about lossless compression. It's always easier to talk about lossless compression, or it makes sense to talk about it first because it's what's used in lossy compression as well. So you obviously, all the lossless compression you can put on top of your lossy compression techniques in order to gain a bit extra, and obviously that does happen here too, and we'll see that in just a moment. And it's the same concept as the audio lossy compression. You want to try and extract and identify areas of, we call them redundancies, but areas of stuff you can't see, basically. So what perceptual information can we throw away in images? The same way as we're trying to throw away that same information in audio. And I was just making the point that with PNG, that's a particularly good format. I mean, obviously it stands for Portable Network Graphics, and we understand that it's lossless at this point. It's perfectly good for lots of different file formats, or lots of different image types, I suppose I should say. Things with lots of blocks of color, logos and all that kind of thing. We saw that it really compresses that kind of thing really well. What it doesn't compress very well is stuff with lots of visual noise, lots of changes in pixels, lots and lots of high detail content. Those things don't contain any run lengths, and so it's impossible to really losslessly compress those. And so photographs in particular represent a really big challenge in compression. So we're going to look at Jpeg today, basically, which talks to that problem. It's a specific codec, it's a specific image format that's supposed to solve the issue of photography. So we're going to build to that. So the first thing I'd like to talk about then is something called chroma subsampling. So this is one of the techniques that goes into Jpeg, and it is an optional technique. And we're going to have a look in the seminar session in just a second look at what differences it makes and how it can be a good thing or a bad thing, and how it works. So it's an optional technique you can build on top of your compression scheme. And it depends. The reason it's optional is because for certain content it does make a difference, and certain content it doesn't at all. And we'll see examples of that. But the basic principle is that when you're testing human vision, you are much, much more sensitive to contrast, brightness levels, than you are to color. Our color sensing system actually really sucks compared to our contrast. Obviously, it's hard to imagine a world with more gradations of color. Certain people do have more gradations of color than others, and actually that was something I was thinking about doing for this, and I forgot about it when I was developing the stuff for this lesson. There are certain people that have got better color resolution, basically. They can resolve between gradations of color more than others. But in principle, most of our color sampling or color vision sucks. So we know that we have rods and cones inside our eyes. Well, we have 120 million rod cells per eye, apparently, which are the ones that sense they're specifically optimized for brightness. So they're sensing contrast, essentially, brightness and darkness. And compared to that, we've only got 6 million cones. And those 6 million cones are spread into the 3 different colors that we can sense, the R, G, and B. So those 3 colors are what we can sense. And obviously, there are a lot more colors in the world. There's a lot more stuff that's in the ultraviolet and infrared spectrum. We don't know what those colors might look like, and it's always very interesting philosophically to think about that. But the basic principle there is that our resolution of our color isn't very good. So it's not a very sensitive system. So what that means for us is that if we are making photographs, or we're trying to crush down the amount of space that something's taking, we can get rid of some of the color information and we can get away with it. So if we are to sample something and have perfect brightness, perfect color, then it's almost a waste to have the perfect color, because you can lower that resolution and your eyes aren't as sensitive and they won't see the edges of it as much, is the point. So if we can take a photo and make sure the brightness is correct, we've done most of the job, and then we can just drop in bits and bobs of color and it will look similar. And that's what we're going to look at, as you'll see it come together in this again. So we've only got 5% of our photosensitive cells that can detect color, so a very small proportion of our eyes are doing that job. And on top of that, rods are much more sensitive as well. So there's a huge disparity. So there's a lot more rods, and they're also about 25 times more sensitive to light. That's obviously kind of natural because the rods are trying to detect all light, essentially, in the visible spectrum, whereas cones are specific to certain parts of the bandwidth. So you're band passing certain sections of the energy. So they're just not as sensitive, they're not as good. So there's a massive color discrepancy there, and we can get rid of color, basically. And chroma subsampling is the job of getting rid of color using a specific method. Now, this represents a problem to us because we store, or we have been storing and thinking so far in red, green, blue, RGB. And we do that because we have cones in red, green, and blue. And so what we're doing is we're storing or thinking about the brightness of red. So if you think about we'll see it in the next slide, but if you think about an image broken into red, green, and blue, you've got a red slide, which is the brightness of the red subpixels. You've got a green image, which is the brightness of the green, and you've got the brightness of the blue. So that is a perfectly good system, but that doesn't allow us to separate out the brightness alone and deal with that separately. So what we need to do instead is try to move to a different, what we call color space. So a different color mode or color space allows us to describe an array of pixels, like an image, in something that isn't just red, green, and blue, and how powerful those three things are. And instead we can move to something, we call it YUV, which we'll see what that means in a moment. So this maths looks scary, it's matrix maths, and to be quite honest, I'm not very good at maths, so I look at that and it kind of terrifies me slightly. But what it means is that in order to get the Y channel, which, as a spoiler, is our luminance value, our brightness value, we need to times our red, green, and blue by, the red is by a third, roughly, the green is by more than that, and the blue is by hardly any. And that gives us a transform between red, green, and blue and brightness. So that's how we do that. So we can take our red, green, and blue channels, times them by those numbers, and then put them all together, and that gives us a brightness across the whole image. We can see that here. So this is from Wikipedia, and it's a really good example, and that's why I've stolen it. It's also not egregiously high in resolution, so it's nice and easy to see what's going on. Here you can see you've got red, green, and blue channels, and it combines to make the color. And if you take the Y, you essentially just get the black and white out. This is the luminance or the brightness. Now, when you look at those, question for you, there's nobody else to answer. When you look at those, which one's the brightest of the red, green, and blue?
The blue.
I think the blue? Well, no, if you just...
Well, when you times it, it's not.
No, but if you look at that, does that look brighter than...
No, yeah, the green's the brightest.
Green's the brightest. Followed by...
Red, then blue seems darker, yeah.
Now, the reason that is happening is because your eyes are more sensitive to green. So your eyes are most sensitive to green and least sensitive to blue. So those are all similar in terms of their actual linear values, if you think of it that way. But perceptually, the green's much brighter. So for that reason, if we're going to extract this channel here and get just the luminance, the brightness out, we need to apply a higher weighting to the green. That's why that happens. And less of a weighting to the blue. And so, yeah, we end up with this Y channel, and the Y channel is luminance. Can't remember why it's Y, and I can't remember why it's U, and I can't remember why it's V. So don't worry about that too much. We're going to look at the U and V in a second. But the basic principle there is we take the red, times it by nearly a third, take the green, times it by nearly 2/3, essentially, and then the blue is left with that little bit at the end there, times them all together, and it gives us a representative. And obviously those numbers came from somewhere. I imagine it's empirical testing. But you can say, well, how bright is that image and how bright is that image? And the idea is they should be the same brightness. So it's a bit sort of fiddly. Yeah. Like it's not a nice, clean transform. It's obviously, there's human perception built into that, basically, is the point. But the essential point is that that's why it comes from. And that gives us our grayscale image. And if we're converting from RGB into black and white, that's the process. That's all we need to do. And this is the kind of stuff that your camera will do. If you say, I want an image in black and white, it will be doing that. So quite useful. So we've got black and white. What about color? I was trying to find the bit where I wrote about the TV trick. So the reason this is an old TV trick, and I was supposed to ask the question here, if you think about what happened in TV world, you had TV was invented, and it was this, just in brightness. Now, we have to think, right, what are we going to do then in order to add color to the situation? We could either send this and then separately send this, which is essentially four channels of information. And you'd have to be able to grab all three of those and put them together, and you'd end up with this. Or if we can take the brightness information, which we've got because of this, and then do some magic to it in order to turn it to this, then that would be more efficient. And that's what they did with color TV. So when color TV came along, it kind of had to be backwards compatible. You can't really expect people to send entire copies of a signal. What you do instead is you send the black and white signal and then some stuff on top in order to be able to convert it into color. And that's where this comes in. So sticking with the idea of three channels, what you do is you send your luminance, which is your Y, and you send a U channel and a V channel as well. Now, the V channel and the U channel aren't the brightness of red and blue. It's quite hard to visualize and conceptualize, right? So what we're used to is this, where you're sending the brightness of a pixel in red and blue. In UV, though, you're sending in what is essentially blueness and redness.
Right.
You don't have to send the magnitude of that, you're just sending the color of it. So you're not saying this is very red, or it's very bright red. What you're saying is this is the color value, it's fairly red. And that's, like I say, it sounds silly, but if you look at what's happening here, if you look at this V axis, this is redness. And if you look at the U axis, this is blueness. So if we go down to where the U axis is making no difference, we're down here. If you go very red, you get to red. And if you go very not red, you get to green. So by going on that axis, we can describe red and green. If you look at the blue axis here, the same can be said if we get rid of all the redness. Yeah? Kind of make sense?
Yeah.
So if we get rid of all the redness, we can go between blue and green. So by having two axes, which are essentially our two channels of video or image, we can dial in and mix between the two of them and get a color value for any given pixel. Now there's no brightness on this. So if you want to go for gray in the middle, this would give you white if you were high brightness. This would give you black if you were low brightness. Or anything around here. So this describes all the colors that you can get, and then you use the luminance channel to describe the brightness of it. So again, it seems quite weird and quite hard to conceptualize, but that's essentially the way that it works. So you have a redness channel and a blueness channel, essentially. Kind of typeset that a little bit wrong. You have negative numbers, so you can have the negative impact of red becomes green. The negative impact of blue becomes green, essentially. And so you've got red, green, blue, magenta. And so they call this, the generic term for this is YUV, color space, or color mode. The terms that you tend to see thrown around, though, are either YUV, or they can be YCBCR or YPBPR. CBCR is the digital, what's notation? So if you want to describe this phenomena or this use, it's CBCR in digital, and PBPR is the analog one, which is how we got color TV. So YPBPR is how color TV came along. Now again, this is hard to conceptualize. It kind of seems a bit nuts, but if you look at the way these channels are actually, how they come out, when you look at them, they look like this. So you can obviously see the blue sky has got a lot of your blue channel in it, so it's down here somewhere. And then it's got lots of negative red in it, so it has less of a red effect, essentially. So this is probably ending up down, where are we? The red channel's here, so probably down here somewhere. And if you combine the two, the blueness and the redness, you end up over here somewhere. So it actually takes those two parts and then gives you this, and that becomes the sky color. So that's kind of interesting. And obviously you've got redness, and when you see the barn there, like I say, it's a good image because you've got this brown, sort of reddy brown color here, so you can really see that shine through here. You're not caring about the brightness of these images. You can see that the actual luminance value across the entire thing is the same. So it's not how bright is it, like the mountains don't look any brighter. So it's kind of odd. You're very used to seeing like bright images and red, green, blue channels to shine out in those specific places. So we do this, right? A whole bunch of magic. and then we get to this YUV color channel stuff. So we did all that, and so instead of having these red, green, blue channels, which describe your pixels, we have YUV color space, which gives brightness and the two color channels. And then once we crunch that down again, we end up with the same color pixel anyway. So it's a new way of describing exactly the same thing, but the key thing is we can separate this stuff from this stuff. Now that we've done that, we can basically lower the resolution of these two images, and they will look just as good as this. That's the point. In order to do that, there are a number of methods. So this notation is always really confusing to me, but it basically means for every 4 pixels of space in pixel space, you've got so many horizontal and so many vertical. No, that's not true. You've got so many on the first line and so many on the second line, right? So this is color information, these 2 second numbers, and this one's here, luminance. Again, I don't know why they chose 444. I don't know why it's not like it's just a weird ratio. But what it means is if you go 4 pixels along and 4 pixels along, if you've got 444, for every 4 pixels along that group there, you've got separate colors. And for the second 4, the next line down, you've got the same thing. Because this was discovered, and obviously this is a TV thing as well, so TV goes line by line, and it was discovered early on that if you basically just ignore every other line or just smudge the color down through the lines so that you don't have a unique color set on every line, you're halving your color information there and not really noticing it. So that was, it's a very TV-based thing. So 444 is where you've got 4 luminance pixels of information. The second 4 means the top one, you've got 4 chrominance, and the second 4 means you've got 4 chrominance on the bottom. So this is full color, full normal stuff. 422 means that for every 4 luminance, you've got 2 chrominance, and you can see that instead of it doing this, we just, copy it over. So you just smudge it over. Sometimes this is averaged between those 2 pixels or something. Sometimes it's just copied over to the next one. There's multiple ways of doing it. And then 2 means that you've got 2 here as well. So in that 4 by 2 block, you've got 4 luminance, 2 chrominance, 2 chrominance. And you can see the difference that it makes, and it looks terrible. Like when you look at it this closely, you think, wow, that's awful. Like, how do we ever get away with that? Because this is what we're after, right? You've got dark pixels there, which represent the red ones, and you've got light blue ones. So this is kind of what we're after. And the net result is you end up with something like this. That looks terrible, and you think, well, how are we ever getting away with that? But we do. And then the same thing, 420 basically means that you get 2 on the top, so 2 pixels the same as this, but you just don't get any extra ones on the next line down for 0. So basically, we just forego an entire line's worth and just copy it down, so you end up with a 2 by 2 block of pixels. And then you've obviously got other ones as well, 411. So 4 luminance gives you 1 chrominance, and then 1 chrominance on the next line down too. So you can basically pick your horizontal and vertical resolutions of color. And I think there are some studies, I'm not entirely sure on it, a little bit sort of unclear on it, but there are studies that say like, human eye is better at certain colors or certain directions of color. So that's kind of cool. So we can do that now. And by going to a 2 by 2, 422 model, we're halving the chrominance or chroma information, saving a whole bunch of space. One of the magic things about this too is that if you think about how we're doing things like dictionary coding and we're taking like known pixel values, by halving these, you're obviously also halving the opportunity for there to be brand new colors. And that reduces or increases the compression ratio. So that's what we call chroma subsampling, reducing the chroma or the color information separate to the luma. So that's the first big win, right? So we do that with Jpeg. Now the second one is that the other big redundancy that we've got within our vision system is that highly detailed images, we are less sensitive to really high frequencies of change of color. And we're most sensitive to big changes in brightness. Same concept, really. We have a very high, a very low threshold of noticing, basically, when we've got very big changes in brightness. So, I mean, the question here is, how would you describe what a bad JPEG looks like? So you've seen a bad JPEG. If you really crunch it, I mean, there's one there.
Yeah, just pixelated.
Yeah, I mean,
Chunky.
yeah, chunky, blocky,
Yeah.
goes blocky. Now the reason for that is, there's lots of stuff going wrong in this image, even in the first frame, but you're not noticing it because it's all very high frequency. And there's lots of stuff like on the edges that's all scuffy and nasty, but you don't really care or notice because it's all high frequency stuff and you don't notice it very much. That's what was happening last week when we did that progressive images, when we loaded the progressive images. The image seems to load and looks fine, and then it goes through and gives you more high frequency detail, and you can't tell, can't actually tell. So that's quite good. That means we can throw away some of that high frequency information and get away with it, but the more we throw away and get towards low frequency, so like bigger chunks, these chunks are different brightnesses, and so you notice them more. So when you look at a bad JPEG, you notice it looks blocky because each block is a different brightness level, and you see that. So if we take it too far, obviously that happens, and that's a bad thing that happens in the world of JPEG. So we need to come up with a way of selectively throwing away high frequency information, basically. That's the gig. To do that, this is where the magic comes in. This thing here is the most elegant and beautiful piece of maths that you're probably going to come across. I mean, not to be a big nerd about it, but it's cool. It's magic. It's magic computer science stuff. So it's very similar in the way that it works. If you think about what we're trying to do here, we're trying to change something into frequency information. And we had the same challenge when we looked at the Fourier transform. We were trying to take sound and samples and turn that into frequencies, if you remember. If you take a whole bunch of frequencies and stack them up, you can make any sound wave. Same thing is true here. So what we're trying to do is we're taking blocks of 8 by 8 pixels, which is just what's chosen in the standard, and that's why it looks blocky. You take 8 by 8 pixels, and what you do is you codify them or code them to say what their frequency content is. And these are the frequencies. This is just in the horizontal direction to keep it nice and easy to understand, first of all. But if you think about what frequency is, this is it changing very quickly in frequency. So you're going up, down, up, down. So this is like you looking at a wave from the top. It's coming up, and then it's going down, coming up, going down. So these are frequencies in waves across here. And you can see the frequency is very high on the right-hand side, and then as we go towards the left, you see the peaks and troughs separate out a bit more. This is like, one peak in the middle, one peak at the sides. And then it gets more and more and more. And then this, we call it DC. It has no frequency, same as electronics, same as audio. If it has no frequency, it's direct current, it's DC. So we call it the DC block. So the worst case scenario in the world is if we change the DC block, because then we're making blocks appear in our image and it looks bad. So we are breaking this down using, again, something amazing called DCT, the discrete cosine transform. We're breaking it into cosine waves. So each of our 8 by 8 blocks gets broken down into cosine waves. And then we can use those frequency elements. They call them basis images or basis transforms. There's a whole bunch of words. But essentially, they're frequency content. We break them down into both horizontal and vertical. And then we basically take those and decide how much of each of them we want to add into that particular block of pixels. And we rebuild it in the same way that we can rebuild a square wave from sine waves. So it's kind of cool, kind of magic, right? So this is the horizontal one. This is the whole lot. I didn't want to show you that straight away because it looks kind of nuts.
Yeah.
But you can essentially see that if you go right to here, you've got maximum frequency this way, maximum frequency that way. They're kind of like room modes. They're kind of like room modes across a room. So what we are doing with this DCT is it goes through and it says, right, so for that 8 by 8 block of arbitrary pixels, we need how much of this, how much of this, how much of this, and we basically drip in various amounts of this. So that one there, we'll say how bright is the entire box itself with no frequency information, essentially. Then we go to the next one along, we're like, how much of this is in that particular image? And again, the maths is nuts and I don't understand it, but it basically is doing that. It goes through and says, oh, how much of that, how much of that, how much of that? It goes through the whole stack and says, how much of each of these do we need to add in order to make that load of pixels up again? Now this thing here is it doing it step by step. So these look a bit blurry because when you zoom in on these things, it kind of anti-aliases them a little bit and it looks a bit blurry. But essentially what you're doing is this, and it's how much of each of them. So there's a letter A that we're trying to form here. and it's 1.042 of that, and it's 1.242 of that, and it's, you know, sometimes it's negative. So sometimes, sometimes you know, if, yeah, so you say, oh, you know, we don't want that, we want the opposite of that, so we'll just negative a little bit of it.
Yeah, that makes sense.
And it slowly goes, well, this slowly goes through it, but it drips through them, and it adds them and takes them away, and then you see this character forming here.
Yeah.
And it does look a bit blurry at the end, but again, that's because it's zoomed in and it's a bit anti-aliased. But that's what it's doing. Again, that's taken from Wikipedia. There's some really nice images on there. I hadn't found any better ones, basically. And you can see by the end of it, like I say, it does look blurry, but we're starting to like hollow out that little A section in the middle there. Some positives, some negatives, a bit of that, a bit of this. So these numbers here, we call these coefficient numbers. So what's the coefficient number of each of these? And like I say, these are called basis images, basis functions. So they're just different frequencies.
So it's almost like layering it, isn't it? Like,
yeah.
Each step.
Yeah. And one of the things I was thinking about doing for this was get everybody to layer up like a big Photoshop session and just layer them.
Yeah, you put them on top.
But that seems like a lot, and I'll probably spend a whole day trying to get that to work, and it won't fucking work.
I know what you mean there.
Yeah. But you see how I think this is magic?
Yeah, no,
it's crazy.
Cool, yeah.
And so this is how kind of Jpeg comes together. So the cool thing about this is it's the same as Fourier theorem. If we take Fourier and we have an infinite number of these, and we have an infinite number of like accuracy, we can get perfectly back to where we came from. So it's lossless. But Jpeg's not lossless, right? That's what this slide's saying. So in principle, this is lossless exactly the same way as FFT is. Obviously, there's a limit to it because we can't go infinitely in every direction. But you could also say that we can't get any higher frequency content than that. So it's the same as Fourier in hearing and sound. If we have high frequencies, that we can't see them anyway. So as long as we have perfectly accurate numbers of these, then we can kind of get it back to lossless. So in doing that, we've not actually saved any space. So how do we save the data? What we do is we try and get rid of the elements of this, or ignore the ones that affect the image the least. And we do that using this. So the top left, this zigzag pattern here, we'll see how that comes into this in a moment, but the top left here, this in principle is the most important because it's the lowest frequency, and our eyes are least sensitive to the highest frequency information. So usually we ignore in this way. So we ignore this as we go up through, essentially. So that's the principle of how this is going to work. We ignore as much of this as we can, starting from the bottom right and going up to the top left. The most important one is the top left one, the least important one is the bottom right one. So we need a mathematical way of doing that, basically. And you could just have a quality slider, and I think some JPEG systems work like this. You know when you save a JPEG, you've got like a quality slider, often?
Yeah.
That quality slider is basically selecting how much of this to ignore.
Oh, right.
It can be. That's one way of doing it. So if you have all of these in a row, can't remember how many there are. 8 by 8, 64. So if you have all of those in a row, you can just say, right, I'll start ignoring from this direction onwards. So you can do that, and that would give you, a quality slider, essentially. But there's a cleverer way of doing it. The way in which this is really usually done is by a thing called quantization. So what we do in quantization is we have some set quantization tables, which are these. What you do is you take the numbers that are coming out, so your the numbers that come out of your coefficients, you have those in a table like this. So this is perfect, perfect DCT. You divide them by your quantization table, round them to the nearest integer, and then when you decompress them, you times them by the same quantization table, and they come out similar. Does that make sense? So you take these numbers, divide them by these numbers, and then go to the nearest integer. Because the numbers are larger in this corner here, more of them get close enough to 0 that they get rounded to 0, basically. And for any given image, most of the time, and we'll see this in a second, I've got like a really good demo that you can use, the stuff up here is most important. When you click an image and find a chunk of pixels and do the DCT, these ones are busier, they've got more content. The ones down here are nearly 0. So the idea of this quantization table is basically to set more of them down this corner to 0. and that's the principle. These quantization tables, there are lots of them. They are developed, I think they're developed kind of heuristically like we saw before. So your settings, as you go up and down your Jpeg slider, just select different, more aggressive quantization tables, as far as I understand it. And the more aggressive they are, the more likely they are to set these ones to 0, and it kind of gets worse in that direction. So it's the same thing. You're ignoring more of these, basically. And then what we do is we reorder all of those coefficients, and we do it via that zigzag pattern we talked about. And we reorder them that way. So we start with the top left and go on this way, because chances are, by the time you get to about here, the rest of them will be 0. And then you've got a huge run length of 0, and instead of saying 0, 0, 0, 0, 0, you just say 15 zeros. And that compresses things down the same way as they do with run length encoding, the lossless compression system. It basically filters it nicely so that lossless compression could come in and finish up. And it does that for every single 8 pixel block on the entire image. So it's pretty busy. So that's how that works, right? Now, on the Sol page, there is a thing to fire up, which you can check out for a bit. I mean, obviously, it's just you and I here, so you don't have to stress about going through the whole thing. But there is something that's worth looking. I developed a little thing, basically, that does a DCT for 8x8 image blocks when you click it on an example image. So you can click an example image, it will show you that image zoomed in, and it will show you what the DCT looks like. So check that out. So fire up for the Sol page and check that out, basically.